Hello, everybody. It is an honor for us to introduce our scientific paper at this international conference in the field of thermoengineering. The name of the article is "The Influence of Buoyancy Forces in Multi-Story Building on the Efficiency of a Regenerative Air Handling Unit with Heat Recovery." The authors' names are Angel Penev and Lubomir Tsokov, and we are from Bulgaria, Technical University of Sofia, Department of Thermo and Refrigeration Engineering. Let's begin with a short introduction. Fixed regenerative heat exchangers are used in ventilation system for heat recovery of the exhaust air from the room. Compared to industrial regenerator, which operate under almost constant conditions, regenerator in ventilation system operate under variable climate condition, variable temperature, humidity, and especially the pressure difference in building. These variable conditions lead to unbalanced regenerator, or in other words, to unbalanced operating mode related to the different value of the regenerator's efficiency. The difference between the external pressure and internal pressure in the building is the stack pressure, the pressure difference, created naturally by density difference from the air temperature change, or also called buoyancy forces. Unfortunately, these buoyancy forces in multi-story building influence the efficiency of the regenerator and create different airflow into the air handling units and different air change rate on different floor of the building. For this reason, we present the three-dimensional computational fluid dynamic model (CFD) to study the different airflows in multi-story building with the natural ventilation coupled with mechanical ventilation with operating regenerator fan. Results show the influence of buoyancy forces in five-floor building on the operating mode of regenerative air handling unit. The next slide is the model statement, geometry and mesh. The geometry and the dimensions of the honeycomb regenerator and the building are shown on the screen. The building has got five identical rooms connected to the one common chimney vent. As you can see, the regenerated air handling units are integrated into the outer wall of the rooms. The main components of the device in this simulation are ceramic matrix and reversing fan. All regenerators are presented as a five single domains connected to the main computational domain with five inlet vents specified with equal loss coefficient, which are explained on the next slide. Problem statement of the CFD model and boundary conditions. The model is steady-state and describes a 3D turbulent flow induced by mechanical and natural ventilation, coupled with underfloor radiation heating, which creates the stack pressure between outdoor and indoor pressure. Sorry. The assumptions made for the model are the air change rate by infiltration is zero, the values of atmospheric parameter are constant, and the wind velocity is zero. The air handling unit is modeled as an individual domain with a constant pressure loss coefficient, which describes the resistance of the system, and the used equation is shown on the screen, where delta P is the pressure drop, ρ is the airflow density, and v is the velocity of the minimum floor area. And the fans are specified as a polynomial function The relationship between the fan pressure and velocity. The numerical simulations were performed at outdoor temperature and pressure. The heat source allocated on the floor of the room with a constant temperature, and the heat flow through the room is modeled by convection and radiation heat transfer, and all the rest walls are assumed to be adiabatic. The graph on the slide shows a fan curve and three resistance curves of the system, defining 3 points A, B, and C. Point B presents the modes of the fan in either temperature condition, when the indoor temperature is close to the outside temperature and the buoyancy forces are negative. Point A and C are present when the indoor temperature is higher than the outside temperature, which leads to buoyancy forces in the flow and displays the resistance curve of the system. Point C is the point of the fan when the direction of the airflow is through the room air supply direction, and point A is the point of the fan when the direction of airflow is to the atmosphere air exhaust direction. The slide 5, the numerical results. The present results describe the system of three different modes of the air hand unit fans: supply air normal fan direction, exhaust air reverse fan direction, and not working fan stack effect. For the last case is presented to show only the influence of stack effect on the temperature and velocity distribution in case of free open inlets only. For example, air handling units without ventilation close valves. The pressure distribution at different operating modes of the air handling unit and the thermal distribution in the building in case of not working fan are shown on the screen. The distribution shows the difference between the indoor and outdoor pressure for each mode of the system. Next slide shows velocity distribution at different mode of air handling unit. The simulation results give the value of the velocity airflow rates for every single room of the building in corresponding conditions. The average value of the velocity are shown on the screen for the mode of normal fan direction, for reverse fan direction, and for only stack effect without operating fan. The change of the air velocity in the regenerator, respectively the magnitude of airflow, affect the air change rate in the room, and in addition, it strongly affects the temperature ratio of the regenerator. The variation of the inlet and outlet temperature during the operating of regenerator at three different floors of the building are shown on the slide. The curve in figure were calculated based on the CFD model presented in our previous work 6. The graphs present the inlet and outlet temperature for most of the regenerators with half period of 19 seconds, and the regenerator reached the quasi-steady state regime after 8 switches. The numerical result of the value of the temperature ratio for the true direction of the airflow in the air handling unit are shown in the table, and the temperature ratio were calculated by equation on the screen. As you can see, when you get to quasi-steady state regime, the values of the temperature ratio during the heating and cooling period are strongly unbalanced, and they have different value of the floors of the building. So The conclusion of this article are right on this last slide. The CFD model can be used for numerical experiments to optimize the performance of the regenerator. The unbalanced mode of operation of the regenerators, influenced by natural ventilation, results in bad thermal efficiency. Various values of the air change rate on different floors of the building and cannot be ignored in multi-story buildings. This leads to necessity of choosing a new control system and components for this type of decentralized ventilation units. We would like to thank you for watching the presentation, and we hope that you understand the essence of our article. Wish you good luck and health, and regards from Bulgaria. Thank you again.